Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we'll be presenting about our topic, which is retaining structure for our case study for BQS 552 construction technology. But before we moving forward about our topic and case study, let me introduce our group member first. First, my name is Aiman Hafiz bin Muhammad Hussein, and then we have Ahmad Alif Amin bin Zamri, Muhammad Nur Salam bin Salman, Afif Firdaus bin Husni, and lastly we have Ajwad Shabil bin Muhammad Adlan. Our selected project for case study 1 is Tone Razak Exchange or TRX. This presentation focuses on retaining structure, system adapted in TRX project, the factor influencing the design, the construction sequence, challenge encountered during constructions, and the engineering solution implemented to ensure a safe and successful excavation. For the first case study, let me begin with project background. The Tun Razak Exchange or TRX is a Malaysia's first international financial district located in the heart of Kuala Lumpur. The project covers approximately 70 acres of scope and consists of office tower, residential building, hotel, retail spaces, public park, and underground infrastructure. Due to dense urban environment and deep basement excavation, the project requires an advanced retaining structure system to ensure the safety of surrounding buildings and infrastructure. For the parties involved in the project was developed by Ministry of Finance Malaysia, which was responsible for managing and overseeing the overall development. The main contractor was WCT Holding Berhad, which was responsible for carrying out the construction work and coordinating site activities. The architect was Leonard Design Architect, who designed the building and ensured the project met functional and aesthetic requirements. The cost consultant was WT Partnership, which was responsible for cost planning, budgeting, and cost control throughout the project. With effective collaboration among all parties was essential because the project involved complex excavation works in a busy city center. Moving on to the retaining structure system, TRX adopted an anchor secant pile wall system as the primary retaining structure. The system consists of reinforced concrete secant pile that overlap with each other to form a continuous wall. Temporary ground anchor were installed to provide additional lateral support during the excavations. The system was selected because it offered higher structural stiffness, excellent groundwater control, and minimized ground movement, making it suitable for the excavation in urban areas. Next, before selecting the retaining structure system, engineers evaluate several important factors. The first was geological conditions. The TRX site is located in karstic limestone, which contain irregular rock formation and underground voids. This condition can cause ground instability, so the retaining structure had to be designed accordingly. The second was excavation depth. Since the project required several basement levels, the excavation was very deep. This increased the lateral earth pressure, requiring a stronger and stiffer retaining system. The third consideration was groundwater control. High groundwater level can create hydrostatic pressure and water seepage. So the second pile wall was designed to provide effective groundwater control. Finally, surrounding environment had to be protected. As the project is located in center of Kuala Lumpur, the retaining system had to minimize ground movement to protect nearby buildings, road, and public utilities. Next, I will explain the construction sequence on retaining structure. The construction began with site preparation, including land clearing, surveying, and setting out the pile location. Next, second pipe were installed around the excavation perimeter in an overlapping arrange to form a continuous retaining wall that resisted earth pressure and groundwater. After that, the excavation was carried out in stages to reduce pressure on the retaining wall and improve safety to workers. At each excavation level, temporary ground anchor were installed and pre-stressed to provide additional support and minimize wall movement. This process was repeated until required excavation depth was reached. After reaching the final excavation level, the construction of permanent foundation system began. This included the construction of pile caps, rough foundation, and basement slabs, which formed the permanent structure support for the buildings. As the basement structure was progressively completed, it gradually replaced the temporary support provided by the ground anchor. In other words, permanent structure began to resist the earth pressure that had previously been supported by the temporary retaining system. Finally, the temporary ground anchor were either removed or decommissioned, depending on project requirement. So in this project case, it will be removed. At this stage, the excavation were completed successfully. Next, this slide presents the main material used in the retaining structure system. The primary material was reinforced concrete, which was used to construct the second pile wall due to its high strength and durability. Next, high-strength steel reinforcement was embedded inside of the pile to improve their tensile strength and resist lateral earth pressure. Next, pre-stressed steel tendons were used for temporary ground anchor to provide additional support and minimize wall movement during excavation. Next, cement grout was injected around the anchor to create a strong bond with surrounding limestone and safely transfer the anchor loads into the ground. Lastly, bentonite slurry was used during drilling to stabilize the borehole before concrete placement and prevent collapse. So overall, this material ensures the safety, stability, and durability of retaining structure.
So, for the next part is I will explain the construction process of the retaining structure used in the TRX project, starting with the plant and machineries. So, since the project involved deep excavation in a densely developed urban area, specialized machinery was required to ensure the work could be carried out safely and efficiently. The main machine used was the rotary board piling rig, which drilled deep boreholes to construct the second pile wall that act as the main retaining structure. A crawler crane was then used to lift and position the reinforcement cage before concrete was poured into the piles. So during the excavation, hydraulic excavators remove soil in stage to maintain stability, while grouting equipment strengthen weak limestone zones and reduce groundwater inflow. Finally, the concrete pump ensure efficient concrete placement during pile construction. For the next slide is I will explain the testing and monitoring carried out during construction. So, testing and monitoring were essential throughout the TRX project to ensure that the retaining structure remained stable during the excavation. So, since the excavation was carried out close to existing buildings and MRT infrastructure, the engineers continuously monitored the behavior of retaining system to minimize any potential ground movement. So, several monitoring instruments were installed, including inclinometers to measure wall movement, settlement markers to monitor ground settlement, and piezometers to measure groundwater levels and pore water pressures. In addition, the temporary ground anchors underwent proof testing and performance testing to confirm that they could safely support the design loads before excavation continued. So, by reviewing the monitoring data regularly, engineers were able to identify any abnormal movement early and immediately implement corrective action whenever necessary. So, this monitoring program play a significant role in maintaining excavation safety throughout the TRX project. Next, I will discuss the challenges faced during construction of this retaining structure. So, one of the biggest challenges was the highly variable limestone formation beneath the site. During the drilling, engineers encountered irregular bedrock cavities and fractured limestone, making the excavation and pipe installation more complicated. So, another challenge was groundwater inflow through these limestone cavities, which could reduce soil stability and increase the risk of excavation problem if not properly controlled. So, beside that, the project was located in a busy urban environment, which is surrounded by commercial buildings, roads, and MRT infrastructure. Therefore, any excessive wall movement or ground settlement could have affected the surrounding structure. So, these challenging such conditions required careful engineering, planning, and continuous monitoring throughout the excavation works. So, how to overcome these challenges? The TRX project adopted several engineering solutions throughout construction. So, before excavation began, detailed geotechnical investigation were carried out to better understand the limestone formation and identify potential ground risks. So, the grouting works were then performed to fill limestone cavities and strengthen weak ground, helping to reduce groundwater inflow and improve soil stability. So, the project also used temporary ground anchors to provide additional lateral support to secant pie wall, ensuring that wall movement remain within the allowable limits during excavation. But at the same time, engineers continuously monitor wall movement, ground settlement, and groundwater levels so that any abnormal behavior could be detected and corrected immediately. So, this solution allowed the excavation at TRX to proceed safely despite the challenging geological and urban conditions. Based on the construction performance of the TRX project, the anchor secant pie wall system proved to be highly effective for the deep excavation works. So, the retaining structure successfully resisted both lateral earth pressure and groundwater forces, allowing the excavation to remain stable throughout the construction. It also minimized wall deflection and ground settlement, which was particularly important because the TRX site was surrounded by existing building, roads and MRT infrastructure that which is need to be protected. Another advantage was the use of temporary ground anchors, which is provided the necessary lateral support while creating a larger walking space compared to conventional internal bracing system. So, this will improve construction efficiency during basement construction. So, for the next part is the cost implication. So, the higher cost was mainly due to specialized secant pie construction, high strength reinforcement, temporary ground anchors, grouting works, and continuous geotechnical monitoring. However, this investment significantly reduced the risk of excavation failure, structural damage, and costly repair works. And they also improved construction efficiency by reducing delays and providing better access for basement construction. Therefore, despite the higher upfront cost, the retaining structure system adopted in the TRX project proved to be a cost-effective solution because it enhanced safety, reduced project risk, and improved overall construction performance.
Assalamualaikum warahmatullahi. My name is Iskandar. Moving on to the case study 2, section 4.0 analysis, we will look at the Merdeka 118 substructure, precision, engineering and retaining system under extreme constraint. As shown in the diagram, our focus is the substructure below ground level down to 23 meter depth, which integrate the diagram wall, foundation and the overall retaining system. Okay, next is the Merdeka 118 challenge, scale and proximity. We face 3 main challenges. First, vertical scale. A 118 story skyscraper standing at 8.9 meter, imposing a massive dead load of over 600,000 tons. Second, substrain depth. A 20 to 20 meter deep bulk excavation to house 5-level basement structure. And last, zero tolerance proximity. The site is situated directly adjacent to active municipal road and transit, low-rise commercial building, and 2 highly sensitive national heritage monument, which is Stadium Negara and Stadium Merdeka. Okay, next for the project consortium, the key stakeholder are PNB Merdeka Venture as the client and developer, providing the strategic vision and funding. Okay, next is Pintras Jaya Berhad as the substructure contractor, executing the D-wall and deep excavation. Okay, next vendor Catsalidis as the architect managing the master planning. Okay, next Arup as the geotechnical consultant handling structure design and instrumentation planning. Okay, then lastly, Jacob Engineering acting as the independent checker for third-party geotechnical verification. Moving on to design consideration. Under design constraint, the Canny Hill formation, 3 critical geotechnical behavior must be managed. First, anastrophic behavior. Highly variable geotechnical properties depending on stress direction coupled with highly erratic bedrock profile. Okay, second, extreme hydrostatic pressure. The 20-meter depth require absolute groundwater control to prevent regional drawdown and soil consolidation. Okay, last, zero tolerance settlement. Any lateral ground movement or stress relief threaten catastrophic differential settlement for the adjacent historical stadium. Okay, to solve this, the retaining system, D-wall and multi-tier strutting was adopted. It features monolithic D-wall, 1.0 to 1.2 meter thick reinforced concrete panel providing an ultra-rigid vertical cut-off barrier with high bending resistance. Okay, next, internal bracing. Multi-tier temporary structural steel strut preload with high capacity hydraulic jack to create active counter thrust. Okay, next, hydrostatic barrier, specially designed hydrophilic water stop at panel intersection ensuring a watertight perimeter. Okay, next, load transfer. Continuous horizontal steel waller beam attach the strut directly to the D-wall face, built using 3-mile concreting with a rebar cage. Okay, this is our hardware and material metric. Pairing raw material directly with heavy machinery. Fluid support, bentonite or polymer slurry is processed by a descending and recycle plant. Second, excavation target. Highly weathered shale or rock is tackled using hydraulic D-wall grab and reverse circulation trench cutter. Okay, next, reinforcement. Grade 500 highly deformed steel cage lift using 100 to 150 ton crawler crane. Okay, next, structural mass. C45 or 55 low head ready mix concrete and PVC water stock are placed via vertical trimming pipe. Okay, now let's look at construction methodology stage, which is cycle process. Okay, first, guide wall. Temporary parallel reinforced concrete wall are constructed to form a precise physical path for heavy trenching machinery. Okay, second, slurry stabilized trenching. Hydraulic grab excavate the trench while high density bentonite slurry is continuously pumped in. This create an impermeable filter cake and provide hydrostatic pressure to prevent wall collapse. Okay, third, reinforcement placement. Massive precision fabricated grade 500 steel cage are systematically lowered into the slurry fillet trench. Okay, continue construction methodology. Stage 2, complete the cycle substructure process. Okay, for 3-mil concreting, high performance concrete is pumped continuously from the bottom up, successfully displacing the lighter bentonite slurry to the surface for recycling. Okay, 5, stage excavation and strutting. As bulk earth is removed, steel strut aligned against water beam and preload with hydraulic jack to counteract earth pressure. Okay, 6, basement slab tied in. Permanent RC rough foundation and slab are cast securely anchoring the D-wall from within, which allow for the systematic dismantling or temporary struts.
Assalamualaikum, my name is Muhammad Yoshabil bin Muhammad Adilan. Thank you, Afi, for your nice and clear presentation. So I'm going to be continuing this presentation and discussing about quality control and automated systems. So in this slide, it illustrates the quality control and automated system used during construction. To ensure internal integrity, concrete cube tests were performed to verify strength, and non-destructive sonic logging was used to detect any hidden voids in the wall panels. A 24/7 wireless network provided special telemetry, including inclinometers to measure wall deflection, tilt meters for foundation monitoring, robotic total stations for surface alerts, and piezometers to track groundwater levels in real time. So moving on to the next slide, this outlines the primary challenges and the technical solutions applied by the engineers. So the main threats included sudden loss of slurry into unexpected rock cavities, which was managed by using advanced polymer slurry additives and targeted pre-grouting of the bedrock. Second, risk of extreme lateral deflection in the soil during excavation, which were addressed by applying hydraulic preloading to internal steel struts. Third, the presence of dense underground utility networks, which required precision planning and 24/7 robotic monitoring to prevent any accidental damage. So, how about the durability and watertightness? So, in this slide, it explains how the site stayed strong and dry. The steel struts kept the walls from moving at all. Also, special water blocking strips were placed in the wall joints. This made the structure 100% watertight, keeping the 23-meter deep pit remain dry and protect nearby historic sites. So looking at the cost, building this way meant spending a lot of money upfront on better tools, strong materials and sensors. However, this was a smart investment. It prevented much bigger costs such as legal trouble, construction delays, or damage to the heritage buildings. So, before we go to the comparison, the Merdeka 118 project shows that massive buildings can be constructed safely in crowded cities with the right engineering. It is now a global example for deep digging projects. So that's all from me. Thank you.
Now, I would like to present the comparison between the retaining system used in the Tun Razak Exchange TRX and Merdeka 118 project. First, let's look at the difference between the two projects. Starting with the project background. TRX is a 70-acre transit-oriented development with a basement excavation depth of 7 to 12 meters. In contrast, Merdeka 118 is a 90-acre development with a much deeper excavation, 20 to 23 meters, for a 5-level basement. For the retaining structure, TRX used a second pile wall supported by ground anchors, while Merdeka 118 used different wall supported by internal steel struts to withstand greater earth pressure. Next, the design considerations were different. TRX has had to deal with column limestone, cast cavities, groundwater, and nearby rail and utility network. Meanwhile, Merdeka 118 was constructed on the Kenny Hill Formation, where the main concern was maintaining zero settlement to protect the surrounding heritage structures. The construction methods also differed. TRS involved installing scam piles, ground anchors, grouting, and stage excavation. On the other hand, Merdeka 118 used guide walls, diaphragm wall construction, concrete placement, steel struts, and stage excavation. Regarding material and equipment, TRX mainly used structural concrete, reinforcement steel, anchor standards, grout piling rigs, and excavation. In comparison, Merdeka 118 required high-grade concrete, grade 500 steel, polymer slurry, diaphragm wall grabs, trench cutters, and descending plants. For testing and quality control, TRS focused on ground anchors, testing and monitoring using inclinometer, settlement markers, and piezometers. Meanwhile, Merdeka 118 applied sonic logging tests, concrete strength tests, tilt meters, and robotic total stations for more advanced monitoring. In terms of cost, TRX was more economical because it required fewer internal steel supports, whereas Merdeka 118 involved higher construction costs due to specialized equipment and extensive monitoring system. Finally, the main challenges were also different. TRX faced cast cavities and groundwater seepage, which were solved through rock probing and grouting. In contrast, Merdeka 118 experiencing slurry loss and wall deflection, which were addressed using polymer slurry and pre-grouting. Now, let's move on to the similarities. Despite using different retaining systems, both projects share several common features. First, both projects use cast-in-place reinforced concrete retaining walls with stage excavation to ensure safe and stable construction. Second, both systems achieve high structural regularity, effective controlled lateral ground movement, and reduce groundwater seepage. Both projects also require a high initial investment but this investment help minimize long-term structural damage, construction delays, and legal liabilities. Finally, both retaining systems were highly effective in protecting nearby infrastructure, maintaining excavation stability, and ensuring the successful completion of this large-scale development. In conclusion, although TRS and Mereka 118 adopted different retaining systems based on their site condition and engineering requirements, both solutions successfully provided safe, stable, and efficient de-excavation for complex urban construction projects. Thank you. In conclusion, retaining structures are crucial for ensuring stability and safety in deep excavation, especially in urban areas. Their selection depends on site condition, excavation depth, groundwater, and surrounding structure. Both case studies show that different systems such as anchored second piles and diaphragm wall with strutting can perform effectively when properly designed and constructed. Overall, successful retaining systems rely on proper investigation, design construction, and monitoring, although they have higher initial costs. They offer better safety, reduce risk, and long-term cost effectiveness. That's all from us. Thank you.